So here, we're asked to evaluate this very complicated looking limit. And, well, indeed, the expression looks really complicated, and, well, paired up with this summation, it's a pain in the neck. However, there might be one particular theorem that might pique your interest. And this particular theorem is called the Squeeze Theorem. You might have heard it, it's very famous in calculus. But anyways, here goes the statement. So if we have sequences an, bn, and cn, and you might be wondering, why am I using sequences? Well, the reason is because this expression here depended on n, and n is a positive integer. So it's more appropriate to treat this as a sequence rather than a continuous function. But anyways, back to the statement. So if we have these three sequences satisfying this inequality chain, and if it just so happens that the limit as n approaches infinity of an and cn, so basically these two boundary sequences, if these two limits happen to equal to each other, call this number L, well then it follows that the limit as n approaches infinity of this middle sequence, Bn, must also equal to L. Now I know that might have been a bit of a mouthful, but in reality, this theorem is highly intuitive. Consider this. I have a graph of all three sequences, and I know these are sequences, so in reality, these should just be points or dots, but I've drawn the line just so that the pattern is easier to make out. So here you see that we have this sequence an, which is always smaller or equal to bn, which is always smaller or equal to cn. Now, we assume that the limit as n approaches infinity of an and cn must approach the same number. So, what happens to this bn sequence? Well, notice that because it is trapped in between these two border sequences, well then it doesn't matter how much it wants to, like, for example, oscillate, or its behavior is basically trapped in between these two sequences. So, as these two boundary sequences go to approach this same limit, well then, this middle sequence is sandwiched and forced to be compressed to the same limit as well. Now, of course, this video isn't about proving the squeeze theorem, but for anyone who wants a more rigorous explanation, here is a proof on the screen which you can pause and read. Alright, so back to this problem. First of all, take a look at this expression. What about the structure of this expression might make you think that squeeze theorem is a potential good candidate? Take a moment to think about it. Well, I really hope you thought to look at this sine of k squared term, right? Because, well, okay, sure, sine of k squared, that's a very confusing term to analyze. However, it's just the sine of something, and sine of anything is going to be between -1 and 1, inclusive. And that is a really good head start to setting up our first inequality, and hopefully using squeeze theorem later down the line. So we can start by setting up our first inequality. We know that sine of k squared is smaller or equal to 1, but greater or equal to -1. Now, here is our hope. Our hope is that we can hopefully perform a sequence of manipulations on this inequality so as to eventually match this middle sequence with the original expression given in the problem. So here, notice that we have a divided by root of k. So a natural next move is to divide all sides of this inequality by root of k. Again, just doing anything in our power to eventually match up this middle sequence. Okay, and by the way, we can do this because k is positive. K literally ranges from 1 to n, so there is no problem. Alright, so now, what is missing? Well, here we have a summation. So with our inequality, we can take the sum on all sides, right? We can take the sum as k goes from 1 up to n on all sides of this inequality. Again, we're just doing anything we can to match this middle sequence with the original expression given. Alright, so now the sum is taken on all three sides. What is missing? Well, notice that here we have a 1 over n. So it's a natural next move to multiply all sides of this inequality by 1 over n. So let's do that, right? We have 1 over n times, and by the way, here, this negative sign can be taken out. So let's just take it out while we're at it, right? We still have this sum, and you get the point. We're just multiplying 1 over n on all sides to finally match up this middle sequence. Alright, so now I'm done multiplying 1 over n, and as you can see, let me just zoom in a bit, this middle sequence matches with this original sequence that we were given. So we are happy. Except not very happy, because look at the squeeze theorem. We needed the boundary sequences an and cn to approach the same value, right? The same limit. And in this case, we can take this as our an, right? Our lower bound sequence, and this as our cn, our upper bound sequence. However, we have no idea what in the world these two converge to. But we know that according to the squeeze theorem, if we want to use it, these two sequences must converge to the same value. So let me ask you, what value should these sequences converge to so as to satisfy that criterion? Take a moment to think about it. Alright, well, I hope you noticed that this over here is just the negation of this. So therefore, if you really want the limit of these two things to be approaching the same value, your only hope is if the limit as n approaches infinity of this sequence, right? You want this to approach 0. That is your hope. Now, of course, we have no idea whether if this is true. But that is the thing with mathematics. Sometimes you might just have to make a claim that feels uncomfortable to make. And that is the whole point of mathematics. You're supposed to step out into the unknown, explore possibilities. So yeah, this is hopefully going to be true, but for now, this is going to be our claim. And if we can if we can prove it, then that is going to be a very beautiful solution to this problem. But for now, of course, we have to focus on this proof of this claim. Anyways, let's proceed. So as a reminder, this was our original inequality, and this is our claim. So first of all, I would like to denote this expression as a function in n, so f of n. And I would also like to note that f of n can be written as 1 over n times 1 over root of 1 plus 1 over root of 2 plus all the way to 1 over root of n. And the reason that I'm choosing to write it like this is, well, sometimes it's easier to analyze an explicitly written sum than a compactly written sum with a summation notation. Uh, for the first reason, I'd probably say that it looks less abstract, I guess. But the second reason is that you get to see each individual terms clearly. Anyways, let's move on. So with this expression, there are two major parts. The first part here is this 1 over n, and that's chill, I guess. But the second part is this series, this sum. And unfortunately for us, there's not really a good closed form formula for us to use on this sum. So that's kind of inconvenient. However, there is one crucial observation we can make, and it's the fact that each of these individual terms are always greater or equal to 1 over root of n, right? Now, what does this mean? Well, it means that this entire expression is always greater or equal to 1 over n, that just comes from this 1 over n. The part that we're comparing is the sum. This sum has n terms, all of which are greater or equal to 1 over root of n. And there we have it. We have an expression we can evaluate. This just evaluates to 1 over root of n. Okay, so now notice what we have derived. We've derived a neat inequality that states that f of n is always greater or equal to 1 over root of n. Now, an inequality in the context of limits problem. What does that make you think of? Well, I'll tell you that it makes me think of the squeeze theorem, right? I mean, think about it. If we can just derive some expression such that f of n is always less than or equal to that expression, well then that becomes a very close recipe for following the squeeze theorem problem solving strategy. Now, of course, the question is, what do we put on this left hand side, right? How do we find this function in terms of n to put on this side? Indeed, that is the question. However, I would like to guide you back to how we found this 1 over root of n. We did it by considering the fact that each of these individual terms are always greater or equal to some particular expression, in that case, 1 over root of n. And that allowed us to calculate a very simple expression to get our lower bound, right? Now, can you follow some similar approach to find this expression to put on the left-hand side? Take a moment to think about it. Alright, so this probably was not the easiest of all tasks. I mean, you might have thought to think of a number x such that n to the x is, well, smaller or equal to 1. And the reason that this is going to be useful, if we can find x, is that 1 over n to the x would be greater or equal to 1 over root of 1, right? And then 1 over root of 1, that's greater than 1 over root of 2, greater than literally every single term in this sequence, right? So therefore, if you can find this x, you can successfully say that over here, this function f of n is going to be smaller or equal to 1 over n, that just comes from this 1 over n, but then we're comparing the sum. This sum has n terms, all of which are less than or equal to 1 over n to the x. And this over here is just, well, n to the x. Not x, but negative x, right? Okay, so this looks pretty nice, but there is one problem. Take a look at this inequality. N to the x is smaller or equal to 1. N is a positive integer, right? So this x is going to have to be negative. Sure, when n is equal to 1, x can be equal to 0, but if we have in general for any positive integer n, this x is going to have to be negative. And, well, if you want this claim over here to be true, you would want the limit, right? You would want, let me zoom in, the limit as n approaches infinity of this expression, n to the negative x, to equal to 0. Unfortunately, this is not true, because this x, well, that is negative, so this negative x is positive, and therefore this would actually shoot to infinity. So this strategy of finding this x for smaller or equal to 1, that is not going to be very effective. However, there is this one trick we can actually leverage. Over here with this sum, we can actually split it up into two parts. So this can actually be written as 1 over n times 1 over root of 1, and then plus 1 over n times 1 over root of 2, plus all the way to 1 over root of n. Now, of course, in this case, this would probably assume that n is at least 2 if you can split it up like this, but if n is equal to 1, we'll just take this part as equaling to 0. But anyways, let's move on. So our goal here is to find some expression such that this is always less than or equal to that expression. How do we do it? Well, firstly, I'm going to leave this part alone, which is just 1 over n, right? But then here, notice we have a 1 over root of 2 plus all the way to 1 over root of n. We can actually leverage a similar strategy to how we used that x earlier. In this case, we can actually define a function r taking in the positive integer n, and let this be equal to a positive real number such that n to the r of n is less than or equal to root of 2. Now, guess what this means? This would mean that 1 over n to the r of n is going to be greater or equal to 1 over root of 2, which is greater than literally every term in this sequence, right? So then, this would mean that we can literally say that over here, this sum is less than or equal to 1 over n. Again, it just comes from this 1 over n. But then this sum has n minus 1 terms that are all less than or equal to, well, this 1 over n to the r of n. And there we have it. We have an expression we can finally put on this side of this inequality. So I've transferred this expression over here. Now, let's consider what happens to this expression as n approaches infinity. Now, first of all, note that for this r of n, well, the way that we defined it over here, right, this r of n just has to be such that n to the r of n is smaller or equal to root of 2. This root of 2 is definitely greater than 1. So therefore, this r of n being a positive real number, that always exists. Anyways, back to our original expression, let's consider the limit. Notice that this expression can be written as 1 over n plus n minus 1 over n times 1 over n to the r of n. And then notice that over here, as n approaches infinity, this goes to 0, this goes to 1. As a quick demonstration of why, this is equal to 1 minus 1 over n divided by 1, if you were to divide the numerator and denominator by n. So obviously, this n goes towards 0, so therefore we just have 1 over 1. Anyways, now that you know why that limit is 1, let's consider this limit as n approaches infinity. Well, because r of n is positive, this would vanish to 0. So altogether, we have 0 plus 1 times 0, this is just 0. So indeed, we see that the limit as n approaches infinity for this sequence goes to 0. Amazing. Now, let's consider the right-hand sequence, this 1 over n, as n goes to infinity. Well, here, obviously, this just goes to 0. And then guess what? Take a look at this. This lower bound sequence and this upper bound sequence both approach 0. So therefore, this entire middle sequence, this f of n sequence, must approach 0 as well. And there we have it. We have finally proven our claim that limit as n approaches infinity of f of n is equal to 0. This is finally proven, which is precisely this original claim, by the way, right? So there we go. We have finally gotten past a major obstacle in our problem, and now we can confidently say that, well, as n approaches infinity for this sequence, well then, this would approach 0, and similarly, for n approaching infinity for this sequence, well, this just goes to 0. And finally, because of the squeeze theorem, as n approaches infinity for this middle sequence, this goes to 0 as well. So therefore, our final answer is that this is equal to 0. And this, well, I've said this way too many times, right? Look at this journey of a solution, right? We used squeeze theorem twice, once here with this inequality and another time with this inequality. So we really did squeeze out the answer to this problem, right? And as for problem-solving strategies, well, first of all, notice that you don't always have to consider the entire expression directly. You can sometimes split it up, and that can still yield elegant structure. And also, notice that, well, we didn't really know what this r of n was supposed to be, but we nonetheless just defined it to be a positive real number satisfying some condition, because we knew it existed. So oftentimes in problems, if you don't know how to find a certain expression in terms of a fixed structure, then consider just inventing it if you know it exists. But anyways, that is the solution. I really hope you guys enjoyed this video. If you did, definitely consider dropping a like and subscribing. Thank you very much. Bye!